ready to start with our program. Let me say a couple things about our program. Nick Tillman, who's our program chair, was the one who came up with this program and said, I heard a fantastic speaker at a conference I went to. It was John Nielsen-Gammon who he heard, and he said, I think we should do a program on weather. And so Nick has been really the person that has been leading that charge. And I'd like to bring Nick up now to introduce our speakers and our program.
All right, thanks very much. It's cold outside. Of course, I knew it was going to be cold because I've been watching the weather forecast. So I was prepared and I wore a tie. Really, I'm going to introduce you to the person who put this together, John Nielsen-Gammon. He's a recognized climate expert. He's a Regents Professor of Atmospheric Sciences at Texas A&M. He's also the Texas State climatologist, appointed by then Governor George W. Bush. And he's an MIT grad. He's earned 3 degrees from MIT, including a PhD in meteorology. John is an ambassador for climate science and for A&M. He writes for the Houston Chronicle frequently. He's also a founder of the Climate Change National Forum, which is I guess it's a blog that I would highly recommend if you want to find out about what's going on and you want to hear from real climate scientists. That's where you ought to go. He's also frequently interviewed in many of the country's leading media outlets: New York Times, CNN, Fox News, Weather Channel, and also international outlets in Australia, Canada, the United Kingdom. On top of all of that, he's really a great teacher, which is probably what he's proudest of. He's been recognized and received numerous awards, including the Distinguished Teaching Award from the Association of Former Students, the Editor's Award from the American Meteorological Society, and he's been named as a Presidential Faculty Fellow by the National Science Foundation and the White House. So, John, I'm going to give it over to you.
Thanks, Nick, and thanks for the opportunity to come here and talk to you about weather and climate modeling without having a filter from the press or from advocates or what have you. And part of the difficulty in understanding what the state of the science is with weather modeling is that everybody has a different conception of what exactly a model is. Go to the next slide. So I wanted to use my introduction time to address that, and then after that we'll have 4 speakers who are all involved in completely different aspects of weather and climate modeling, talk about the state of the science from their point of view and their expertise, and then we'll open it up for questions at the end. So many of you may think of a model as being this. Next. Now, I admit I'm probably not including everybody in the room with that, so go to the next slide. Some of you may have that perspective. And just to be completely general, next slide, please. But in terms of models used in science and technology, let's talk about some specifics. I'll talk about what the model is, what its purpose is, and how it gets, what its goals are. And we'll start with economics models because meteorologists like to talk about economists to deflect criticism. And so an economic model is basically trying to take a set of assumptions, simplifying assumptions about how economics works and how people behave, and you can use it for forecasting, or you can also use it to try to understand what the consequences are of different assumptions. And ideally, you want the model to be as simple as possible while still being able to explain what you want to explain. Next. Biologists have models, which are actual living beings. The idea being that you can't really do all the experiments you want to do on humans, whether it's too expensive, too complex, or so forth. So the model is a stand-in for the other organism you want to study, and again, you want it to match the subject you really want to study as closely as possible while still being as simple as possible. Next. In statistics, we've got statistical models used in all sorts of different applications, and basically that describes how two things are related to each other mathematically based on data. And you've got two possible reasons for doing this. One is to try to make predictions, and the other is try to tease out possible actual physical connections between the different things. And unlike the other models, I think in statistics the goal is really to be as accurate as possible. It doesn't matter how complex it is, as long as it is not overfitting and still gives you a useful bit of information or useful prediction. Next slide. Engineers use models all the time. And they can have two main purposes, I think. One is, again, experimenting to test out different designs to see how they work. But also, you want to know how something is going to perform within certain specs before you build the thing. And so you really need to demonstrate that what you're creating is going to work. And so the goal here, again, is not simplification so much as actually having an accurate prediction. And you generally have some constraints on exactly how accurate that prediction needs to be. Next. So now I'll talk about the models we're going to talk about. They're, again, mathematical representations of how things behave. And most of the models you're going to hear about have two basic components. One is the physical laws that describe how different parts of the fluid interact with each other. That date back to the time of Isaac Newton. And those things can be described exactly, although you can't describe how each individual atom is moving around. You're making general assumptions for a bulk of fluid moving together. And so you're limited by how much of the atmosphere you can simulate as different distinct entities by computer power. The other aspect is, even at that, there are things going on such as radiation, interaction with other surfaces, and so forth that aren't described by the equations of motions, and those are estimated on the basis of observations as to how the things that are happening on a small scale are related to the things that you'll be able to simulate on a larger scale. So those are the two basic components of the sorts of models we deal with. Next. And there are multiple purposes, which you've seen different flavors of already with the other models. One is experimentation, because you generally can't do experiments on the atmosphere. People tend to object to that sort of thing. So you look at how you want a model. You want a model that's able to simulate the thing you're studying, and you want to be simulating it at the process level, not just giving you the right answer, but giving you the right processes. But with respect to the equations that we're talking about, there's just 6 or 7 equations, and yet the atmosphere, which is following those laws, has this complete richness of behavior that lets you study how all these things fit together to form waves, instabilities, whole bit. And that's what we'd be doing if people didn't care about the weather. But people do care about the weather, so there's also a predictive aspect where we want to be able to forecast what's going to happen as far into the future as possible, which is unfortunately physically limited, not by computer power, by model power, but by the way the atmosphere works itself. Next. So we've got these two competing goals. And the goal that most people are familiar with is the forecasting goal, where you want the model to produce the best possible forecast. You don't care how complex it is, as long as it runs fast enough to give you a forecast before the weather actually happens. And then in terms of research, you want the model, here again, to meet these two often competing goals: simulate how the atmosphere is behaving or the ocean's behaving as accurately as possible in as simple a framework as possible, so it's possible to understand what's going on in the atmosphere as well. Next. So you're going to hear about things from both the weather forecasting aspect and from the climate aspect. You're going to hear about not just modeling atmosphere itself, but interactions with the ocean and with the land surface. And you're going to hear about not just trying to forecast future weather and climate, but also trying to figure out what happened in the past and why things worked out the way they did.